portion. It is disgusting.
There's a, you know the TV show Hoarders? There was an episode of TV show Hoarders where they finally started cleaning out like the stash and they found a homeless man living in it, but they didn't know it was there.
Distribute the test at the end of the class, okay? So what I want to do today is give you additional methods to get the second solution. We did the Wronski method previously, and that's useful only if the first solution is in a closed form, right? Otherwise you cannot integrate. So the method that I'm going to develop today is called derivative method. And I'll also talk about series method, which sort of follows immediately from the derivative method. So you can always find the second solution through that method. So most of the time you cannot find a closed form solution, so this method is useful. Okay. So what the premise of this method is as follows. So what I'm going to do today is two methods. Series solution actually, which follows from that method. And I'll also do an example so that to illustrate the method. So that's what we'll do today. So the starting point for this method is follows. If you recall, okay, this is needed when do we need? We need this when the identical solution, right? If the initial roots are identical, we have to get the second solution, right? The other case is when sigma 1 minus sigma 2 is an integer. All right. With sigma 1 is not greater than sigma 2, then we have to find a solution corresponding to a smaller initial root. Okay, so identical roots. And when the difference between the initial roots is an integer, we need to have other methods to get the second solution. So the premise of this method is as follows. We propose a Frobenius series solution, right? I mean, we have already initial roots and stuff like that. That means P of z and Q of z are not, one of them is not well behaved or both of them are not well behaved. And you can remove the singularity. So it's a z equal to 0 is a regular singular point. That's why. The premise of this method is as follows. Instead of, we make the coefficient function of sigma, and we don't substitute for the initial root until, only towards the end we'll substitute and do that. And we know that this is nothing but, this is like Frobenius series, except I'm making this as a function of, the coefficient as function of sigma, okay, the initial roots. So this is one of the starting points of this method. So our goal, is to find the functional form of an, and once we find the functional form of an from the recursion relationship, right? We'll find the functional form, then we can find a second solution very easily. So our goal is to find can we predict the functional form of a and sigma, okay, the coefficients. Now, what are we trying to do? We are solving a second order differential equation. And if you remember, the way we write our canonical form is like this, right? I mean, we are solving a homogeneous second order differential equation of this form, which we can write it in this. I think I introduced this notation previously, where L is nothing but your differential operator. L is nothing but this operator. It's a linear operator. L operating on Y is nothing but your differential equation, right? The way now. So that is. So I'm writing this in a concise notation, and L is nothing but a linear operator. Okay, this is a linear second order differential equation, so L is a linear operator. All right. So what we are going to see is, so that is your differential equation. I've written it like this, but I'm proposing the starting point like this to get the second solution. Y is a function of sigma. Okay, so we want to look at my linear operator is that. What if I operate L on this? Okay, can I sort of guess what it should look like? L is this, right? And Y is now a function of all these things. Y is this, right? I mean, so whatever happens, it has to be a function of sigma, definitely, right? So we know the procedure, and we just have to take the first derivative, second derivative, and all that. So you will have what? Z to the power sigma and some summation to the power of Z to the power n and all these things. We do have, just substitute this into that, or into that. I mean, when I say this, this is what it is, except now I'm making Y as Z's, it's function of both Z and sigma at this point. Sigma is your, will lead to your initial roots. So can I write this as this?
That would be L of the A sub n? Or is that L of the whole thing?
L of the whole thing. Okay, this is what. If you what is the first, whatever I have written, what does it remind you of? When we did that, right? When we did this without this being a function of sigma, right? That's what we did. So what we had, some functions of z. I mean, some powers of z, and the lowest powers of z was what? Initial root equation, right? And the rest of the terms in this power of z, okay, we have, the first term will be like this. Second term will be what? A1 sigma, z to the power sigma plus 1, blah, 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 okay? So those rest of the equation, it has to become 0 eventually, right? Because we want to seek a solution. Rest of them what? They lead to a recursion relationship in A and sigma. That's what it is. So those will be 0. So we can say this functional form of, if y is like this, the functional form of L operating y should be of this form. Okay. So this is the starting point of this derivative method. Okay. You first say, okay, I'm going to start like the Frobenius series, except I'm going to make this as a function of sigma, the coefficients. Then you just say, okay, what is L operating? L is just that, okay? So you will have, term by term when you do it, you'll have several powers of z. But the first term is your initial, that's what leads to initial root equation, right? So from there you can, and we had factorized out previously z to the power sigma out when we were doing an was a constant, and the rest were powers of z to the power n only, and we are looking at the term when n equal to 0 and z equal to 0 to lead to the initial root equation. So this is sort of how you can guess what this behavior of L operating on Y, which is of that form, would look like. Okay, so it's just substituting Y prime, Y double prime, and you have all the series. So if you understand this part, all right. So this is a second step here. Okay, this is the first step, and this is the second step. And let's try to solve for the case sigma equal to sigma 2 second solution. How to get it? That's what we are able to do. So what is it? What is 1 2z for sigma 1 equal to sigma 2? That's what we want to understand. So I'm just, all I'm going to do right now is sigma 1 equal to sigma 2. I can write this as sigma minus sigma 1 squared z to the power. All I've done is nothing but putting sigma equal to sigma 2. And as usual, we'll take A0 sigma to be 1. Okay? So you can take any constant. The first term you're going to take this constant at this point. All right. Now what I'm going to do is take the partial with respect to sigma of this quantity. And we'll examine this partial for sigma equal to sigma 1 or sigma 2 doesn't matter because they are the same here, right? I mean, let's look at this for sigma equal to sigma 1. All right. I know how to evaluate my right-hand side. It's simple, partial. So we'll have two terms. But important thing I want you to notice is when I say this L is with respect to what? What is the independent variable in L? Z. Okay. It's a linear operator. Okay. So I can change the order of differentiation. I can have partial of z and then partial of sigma. I can change the order of differentiation. So that's something that I want you to first notice. That's an important one. So independent variable, because this is nothing but derivative, second derivative, first derivative, everything, right? I mean, independent variable in L is z. You differentiate with respect to z, right there. Now, okay, let's, what about the right-hand side? What is happening to the right-hand side? So if you recognize the fact that we can reverse the order of differentiation, I can write my left-hand side as this. Okay. And what is that quantity? Can I write it as plus, what is the other one? What is partial of z to the power sigma with respect to sigma? What is that? Because what I'm differentiating is in the exponent.
Sigma times?
Hmm?
Sigma times z power of sigma minus 1?
No, that is, no,
Yeah.
no. This is not sigma to the power. That you can do it if it is, yeah. The
Yeah.
power is it's in that, yeah.
Yeah.
So you have to, you put it in
Yeah.
to some variable x or something and
Yeah.
do it 2 times and all that, right? So that is nothing but z to the power sigma natural log of z. Okay, so that's an important thing because the variable that you're integrating, differentiating is in the exponent. So all you have to do is, change the variable and try to do it. Okay, this is the, I can have it, yeah, okay. So that is nothing but, okay, so this is something which will keep on coming. So just, I want you to be careful about it because the variable that you're integrating is here. Okay, it's the exponent, it's not. Exponent is not a constant. We're differentiating with respect to what is in the exponent. I mean, you can just say z to the power sigma equal to t and then take log of both sides and then differentiate both sides. Okay, that's how you do that integration. All right. So this for what is that? What's on the right hand side? That's 0, right? So what can I say about this then? So I have this linear operator on this. Right? This is what we have. So what can we say about this quantity within the curly parenthesis?
It's a
Evaluate.
constant?
Huh?
It's a constant?
No.
No.
L is what? Differential equation, d square. This is nothing but what? D square over dz squared plus whatever p of z, d of z plus q of z. Okay, that's what. You have to remember this as your differential operator.
Is it that the differential with respect to sigma of yz is a solution to the original equation?
Right. If you whatever you said was correct if what? If it was only one derivative, right? It was dy, d over dz of something is 0, that's inside is a constant, right? But this is not d over dz, this is L is d squared over d, that's what I wrote down initially, right? So you have to remember this is nothing but, is representing the entire thing, right? So it's not just d over dz of something or what it is, right? So what it tells me is this quantity, because if L, so that I wrote in the shorthand notation, if you remember, this is my homogeneous, if this is my operator, my homogeneous differential, any homogeneous differential equation would be written like this. That's usually a different second order differential, linear second order differential equation. So if that is 0, whatever I have here is the solution, is the second solution. Okay, so we have constructed a second linearly independent solution, okay, by this method. So y2z is nothing but evaluated for sigma equal to sigma 1, which is your identical group. So why is this? It's supposed to be the Frobenius except this. So what you will do is, In order to get the solution through this method, you will substitute, of course, in your original differential equation and get the recursion relationship, except keep your an, do not substitute the initial root value, okay? You have to keep that as a variable, and then when you look at the recursion relation A1, A2, you have to guess the functional form of an as a function of sigma. Once you have that, then it's a very trivial, derivative to get the solution. Okay, so we'll do an example, it will become clearer. Okay, I mean this is the logic behind the whole thing. Okay, so and what we have constructed is a second independent solution because we don't have a second. In this case, the Frobenius series you applied directly, we get only one solution because sigma 1 equal to sigma 2, right? I mean, so you're not going to get a second independent solution directly from that method. All right, so let's also do the other case. Here also we need a solution, so I'm going to write down here because and you have to remember because Frobenius series kind of. All right. All right, the other case was sigma 1 minus sigma 2 is an integer. The difference between the two initial roots is an integer. Then we have to construct a second independent solution for this case. So what we're going to do is here, all right, I have that, right? Yeah. And we have, these are very standard right now. It's common to both methods. I'm going to multiply this equation by sigma minus sigma 2 L operating on is equal to, again I'll take A0 sigma equal to 1. And sigma 2 is a smaller root here. Sigma 1 is greater than sigma 2. So you have, from the Frobenius method, you have one solution with sigma equal to sigma 1. It's for the other one we have to find out what the solution will be. All right. So same thing, we can make the same argument. This is with respect to z. So in principle, I could write it for sigma equal to sigma 2. It becomes 0, but that does not give you an independent solution because, I mean, I could in principle write it like this, right? Because this is with respect to z, I could write it like this. Because it's almost like a, because I'm differentiating with respect to z, doesn't matter if I pull it inside the differentiation. But we know that for sigma equal to sigma 2, I'm not getting an independent solution. That is my problem. So this will not lead to an independent solution, although it is equal to 0. Okay. So what we are going to do is, again, this is the way people construct independent solution. You just take a derivative, again with respect to sigma, and look what happens to it. So you again take partial with respect to sigma of this whole stuff. I can already reverse it, doesn't matter, right? I mean, or we can, okay. Yeah, and we go to that. Step by step, doesn't matter. Now, then I take A0 sigma equal to 1, okay, then. And I'll take partial of sigma with respect to sigma of all these things. And then examine that for sigma equal to sigma 2. Whatever happens to the right hand side, and this for sigma equal to sigma 2, we have to examine that. For the same reason, I can pull it out. So what left hand side will be nothing but the linear operator pulled out, because this is independent variable z. So I can write it like the linear operator operating on this quantity. And we just look at it term by term, it will be 0. Maybe we can look at it. Okay. Of course, the first term will be, one of the terms will be sigma minus sigma 2 squared, z to the power sigma, right? The other term will be sigma minus sigma 1, and this will be 2 times sigma minus sigma 2, z to the power sigma, plus the last term is, of course, sigma minus sigma 1, sigma minus sigma 2 whole squared, and this term is z to the power sigma natural log of z, because I'm trying to take the derivative with respect to sigma. Okay? So, which for sigma equal to sigma 2 will be 0, all of them have sigma 2. So the second solution we want to propose here, for this case, is the following. Y2z is nothing but partial with respect to sigma of, this is sigma 2 is a smaller root, okay, sigma minus sigma 2 multiplied by yz sigma, okay, and all these quantity you have to evaluate for sigma equal to sigma 2. Evaluate this, that's it. Since I'm already here, I think I'll talk about, I think we can talk about series method now. Yeah, all right. So in this method, so what you'll do is start with that, set up the recursion relationship, and then somehow guess the solution, function form of A and sigma, and then once you have that, all you have to do is take the derivative, plug it back into that and take the derivative, and you will get the solution. Now, since we are here, I want to talk about this. other method, which is just follows directly from here. Okay, so this is derivative method. When it's a series, not Frobenius, just, some series we'll get, okay, we'll look at that. All right. So for the first case, sigma for identical roots, since that is the formula, I can write Y2Z as nothing but YC sigma is that, right? I got two terms here, right? One of them would be what? Z to power sigma, natural log of Z, right? When I take the differential with respect to that term, summation n going from 0 to infinity, a n sigma Z to power n. So that is the first term, plus the second term will be, I got sigma here, right? So I have what? What do I have? Z to power sigma, I have already taken that. So the derivative is with respect to this coefficient, okay, Z to power n. Okay, all these we have to evaluate at sigma equal to sigma 1, so I can change this to sigma 1. Okay, and this is being evaluated for sigma equal to sigma 1. All right. And this is that. And what is this for sigma equal to sigma 1? For sigma equal to sigma 1, it's become this, right? And what about this term? Sorry, and I should put it not that one up.
That's the original answer.
It's y1, right? So what you have is the second solution, it's this always the case, okay? I mean, the second solution is always the first solution, what we got, okay, times natural log of z, that will be your first term, okay, plus this plus an infinite series, on this series, right? This here is, here n equal to 0 to infinity, but I'll also say this, in books you'll say n equal to 1 to infinity, mainly because we take a0 sigma equal to 1 constant, okay? So you'll see it as, constant, so that will be 0. The first term will be 0, so this will be written as n going from 0 to infinity. Now it's become totally derivative. Sorry, n equal to 1. Because, okay, and then we have some coefficient, you can call it as some coefficient Bn, okay? Z to the power, it's an infinite series. That's why it's called a series solution. The first one is, this is also, in principle, that's also an infinite series because natural log of z can be part of a infinite series. So always first solution type natural log of z, that would be the first term. And the second term would be simply so a very concise notation. This will be a solution of any second order differential equation. Okay, you will be when P of z and Q of z have regular similar point, Bn, z to the power of n going from 1 to infinity. Okay, with the coefficient Bn. So that's why it's called series solution. You'll always find such a solution where B1 is nothing but the derivative of these coefficients with respect to sigma. Okay, sigma equal to sigma. That's what you're looking at. And in most physical problem, okay, what will happen is at z equal to 0, like wave function or whatever it is, z equal to 0, this become infinity, right? So you will drop that solution because that's not a physically meaningful solution. So the only solution, many times in scattering theory and quantum mechanics will come across such a thing, okay? Solution of second order differential equation. You will see something like that taken as a second solution in the series form. You don't have to go through the entire process. All you have to do is, you have to know the initial roots and then, calculate something like that. So you know the general form of the solution. That's all I want to tell you. So the series solution will be something like that nature. You can similarly prove for the other case, that is in this case, the second solution, this is identical roots. Or you have to again substitute on that. For the case sigma 1 and sigma 2 equal to integer, the second solution will again be of this form. The first term will be like this, okay, except the second term will be under series, except the coefficient Bn, how you evaluate is different, okay. All right. But this is for sigma 1, sigma 2, right? We are calculating. You will have something, let me call it again Bn. In this case, we can have it from 0 to infinity because of the form of Bn. There also you can do it, doesn't matter, it becomes 0 automatically anyway. So Bn in this case, in the second case is you have to take the derivative of sigma minus sigma 2 times an sigma, and you have to evaluate this differential for sigma equal to sigma 2. Okay. Here you evaluated this for sigma equal to sigma 1, okay, and so in this case you have to take the derivative of sigma minus sigma 2 times an sigma, and that derivative product of this function you have to calculate at sigma equal to sigma 2. Right? Again, it's obtained by, the way you get it is, you just have to substitute in this formula. What you have to do is substitute for that and get it. All right, let's do an example so it becomes clearer what I'm trying to say for this. done this problem before using Wronskian method, the exact problem we had done before. All right, so that's your differential equation. So what are the initial roots for this case? Let's first get the initial root and see whether it's identical or whatever it is. Based on that, we have to choose a formula. So what's P of z?
Three over z minus one.
P of z is 3 over z minus 1.
Yes.
Okay. Q of z,
One over z times z minus one.
and so what happens at z equal to 0? P is fine, but the other one, so we have to use a Frobenius series. So, in such cases, we'll analyze z times P of z and z squared times Q of z as z tended when z goes to 0. And if that is finite, at least one solution can come from Frobenius series. So z times P of z is what? 0. Okay, so that is your S of 0 also, right? And z squared is what? Qz is also 0, right? So that both are finite. Z squared becomes z in the numerator, doesn't become 0 too. Okay, so my initial roots are, initial root equation is what? Sigma minus sigma 1 plus S of 0 plus P of 0 equal to 0, right? So we have sigma equal to 1, sigma 1 equal to 1, sigma 2 equal to 0, right? I'm going to call the higher root as sigma 1 on this, okay? So these are the roots, all right? So I have to use this formula because it is not in that case, I have to use this case. So my second solution will be given by that formula. And we also know that, okay? All these things, or you can use through the AN, that is, I don't know what I did, but you can, one of the two. All right. All right, so the whole goal for me is somehow, in order to calculate this derivative with respect to sigma, I need to get the functional form of A and sigma. That is the thing, and that will come from the recursion relationship. And so let us start substituting it, keeping sigma as a variable. Okay, keep this as a variable, that's all. Initially, okay, we'll do that, and only towards n, we'll substitute. So right now the procedure is similar to what you already know. Y prime I always go back to the original differential equation, even though I might put it in the canonical form, because then I do less algebraic mistakes. Okay, go back to, for substitution, after analyzing P of z and Q of z, I always go back to the original equation, because then I don't have stuff in the denominator and all that stuff. Right. So this is function. Okay, it's not that. Okay. Okay, so we have what, the first term is what, z squared, y double prime. Okay, what is y double prime? Is that? Is that, okay. N plus sigma minus 1. So I have a z square here, so I can make it as z square n plus sigma. Okay, so I'm going to get that's z square I have. Okay, minus z, n going from 0 to infinity, y double prime still, right? A n sigma, n plus sigma, n plus sigma minus 1 minus z, so it is z to the power n plus sigma minus 1. So that is my second term. And then I have, let me just write it here, plus 3 times that, z is multiplied by z, so I have a n sigma n plus sigma sigma n plus sigma n going from 0 to 3zy prime plus y. Y would be that a n sigma is equal to n plus sigma n going from 0 to infinity equal to 0. Right? So right now it looks exactly like what we've been doing so far. And then we look for the same power of, let's look at the power of 0 n plus sigma. Okay? And here that means I have to change n to n plus 1. Okay. So what we have is comparing looking at the term z to the power sigma. Look at the term z to the power n plus sigma. So that will give me a n sigma. This will be n plus sigma square minus n plus sigma is here, right? And I have plus 3 times n plus sigma. Okay. And then that is simply 1. Last time is just 1. Is equal to, where is this one? This will become a n plus 1 I have to change n to n plus 1 everywhere there. N plus 1, n plus sigma plus 1, n plus sigma. That's what we get. All right. So that is a n sigma. This is what, 2n sigma, right? So this is n plus sigma plus 1 whole square is a n plus 1 sigma Alright, so what we have is, this is nothing but a n plus 1 sigma over a1 sigma, or a n sigma is n plus sigma plus 1 divided by n plus sigma. So this is a recursion relationship with sigma as a variable we get, which is somewhat similar to what we always had. From here, we need to guess this, right? Because so I have to somehow get this functional form so that I can take the derivative of y with respect to sigma. Because that's the main thing that I have to do in this method. And we also know that I could take a0 sigma equal to 1. So, so n equal to 0, what do I have? I have a1 sigma over a0 sigma would be sigma plus 1 over sigma. N equal to 1, I'll have a2 sigma over a1 sigma. N equal to 1, right? Sigma plus 2 over sigma plus 1. All right. So what is my, if I wanted a2 or a0, what is it like? Can I, what is, can you guess what this term will be like? So a0 sigma is 1. a2 sigma over a0 sigma is sigma plus 2 over sigma, right? Right? So what is an sigma over, what is an sigma over a0 sigma?
Sigma plus n.
Over sigma. Okay, so I can write it like this. So it's a fairly simple functional form. Since this is 1, an sigma is that. Okay, so we obtained a function form for an sigma. All right, from here, let's go to the how to get the next steps. Okay. So I need to calculate that y to z, right? I mean, I have, this is the formula I apply. Is this clear? All right, so I need to calculate this. Y to z is partial with respect to sigma of all these things. And I can start writing. Sigma 2 is 0, right? This is what we have to do. Sigma equals sigma 2 equal to 0 in this case. All right. Now I can write an sigma as this. I have the function form, so I can substitute here. Sigma plus n over sigma. Okay, I can do that, right? Sigma 2 is 0. Okay, so I cannot substitute for sigma until I do the derivative because I need to. But sigma 2 is a fixed quantity, right? So this is 0. And I have a sigma here and a sigma here. I can cancel that sigma because it's a summation over n. So this one becomes partial with respect to sigma of sigma and all these things. Sigma plus n. I think I can do that, yeah. Z of n plus sigma. Okay. And whatever it is, I have to do this also. Sigma, after taking the derivative, I have to do the substitution.
You said after taking the derivative,
Yes.
but we haven't done the substitution.
Okay. Yeah, we can take, for sigma, we can substitute as sigma 2. The formula says, take the derivative of this whole quantity, okay? And then, whatever you, after derivative, whatever you get, put sigma equal to sigma 2. Okay, to be 0. So I'm pretty sure you're getting, sigma 2 is a fixed quantity, okay?
Right.
So you can, if you can keep it if you want, but it's a constant. What sigma 2 is, it makes my life easier because I can get rid of it, then you can see already, right, there is a sigma then. And that sigma, this sigma I can pull out, okay? So I need to take the derivative of all this quantity. And then after, that's why I want to, and after that, you can put sigma equal sigma 2 equal 0.
So you can only do sigma equals sigma 2. Oh, you're not putting sigma equals sigma
Sigma
2,
2.
you're using sigma 2 already. Okay, makes sense.
Yeah, okay, yeah, I can use sigma 2 because sigma 2 is a well-defined quantity. Sigma is a variable, and I have to differentiate. So you can, let me say sigma equals sigma 2, otherwise you'll get confused, and then you put sigma 2 equal to 0, okay? So this quantity has to be evaluated sigma equal to sigma 2, according to the formula, and the value of sigma 2 is 0. I mean, our initial root is 0, okay, we'll do that. So this now, all right, can I, how to take this derivative because this is n.
Would you be able to multiply the outer sigma into and remove both the outer and
I'm
the...
just trying to see, did I make, this was sigma 2 and oh sorry, this sigma got cancelled, okay? Sorry, this sense is the sigma, it's just sigma plus n, right? Yeah, because sigma 2, yeah, it's had the extra term. Alright, now we can do this, okay? I got two terms, so it's just a summation. Let's, how to do it. I have to worry about this, okay? I mean, there's a term here. This is a term which I should worry about carefully. So let us call this as one term and the other one as other term. I mean, it doesn't matter how we want to do because that's a constant, so it doesn't even matter. So I have partial with respect to sigma of if I took this term of sigma plus, what do I do this? Oh, I can take partial inside. Let me just take this and going to 0 to infinity of, I'm trying to take partial with respect to this term first, okay? Okay, and the other one I'm keeping it as such. Plus, of course this has to be valid for sigma equal to sigma 2 equal to 0. The other term is then sigma plus n, z of n, and that one is what? Z of sigma natural log of z, right? This term becomes that, n going from 0 to infinity, and all this has to be calculated for sigma equal to sigma 2 equal to 0. Okay. Okay, so what is this term? I mean, that is 1, right? Or I can put, let me just see. Get a 1 there. Something is goofy, but just we have to do this carefully. Sigma 2 I put 0, and I was left with the sigma. That sigma I can cancel with that sigma, but no problem because this is independent summation, so I can cancel that. So end up with this, okay? So I end up with that, and then I have, oh, I see. Let me just write down. Let's first do the summation properly, and then. So I have two terms. One of them is sigma. One term is what? Sigma times z to the power of n plus sigma. Okay, that's the first term, right? Plus n z to the power of n plus sigma, n going from 0 to infinity. And then we evaluate this for sigma equal to sigma 2 equal to 0. All right. This one, okay, so this term, I got two terms, that's what we're trying to see. Okay, so that term will be what? The first, I've distributed that. Okay, the first term will be, it looks like I have z to the power of n plus sigma, summation n going from 0 to infinity, okay. Sigma is 0, right? So this is really z to the power of n, it looks like. The first term is z to the power of n plus, do I have under term? That's what I'm trying to say. That looks like an extra term. Partial of sigma. Okay. It is 0 because the other term is 0 because sigma is 0. Okay, so the other term is what? We have sigma times n going from 0 to infinity, partial with respect to sigma of z to the power of n plus sigma, right? I don't have to, because this I cannot do sigma equal to sigma 2 equal to 0. Because sigma is 0, this term, the second term from here is 0. Alright, so then I have one more term, which I have to be now careful. I have n z to the power of n. Okay, I have to take the derivative with respect to z to the power of sigma, which is what? Z to the power of sigma, natural log of z. Okay. Natural log of z. And because sigma is, I have to calculate z to the power of 0 is 1. So what I have is the following. Okay, now just one. Alright, this is my y2z. I'll explain to you in a minute. Okay, so y2z appears to be the following. Summation z to the power of n going from 0 to infinity, plus natural log of z, summation n z to the power of n going from 0 to infinity. So this is your second solution. Have you followed what I have done here? Okay, so this is what we ended up with, right? I mean, up to this point it's clear, right? So I'm just trying to get the first term, sigma times, I'm calculating, separating the two summations first, okay, distributing that. N times z to the power of n plus sigma, okay? And then I have to take the derivative of that. When I take the derivative of that, this has got two terms, okay? One of them is coming from here, okay? And I put, I have z to the power of sigma, but sigma is now 0. I can start, after taking the derivative, I can put sigma equal to 0. So that z to the power of 0 is 1. So that's how I get this. So this term is coming from taking the derivative with respect to that and leaving that term as such. And now, since I've taken the derivative, I can put sigma equal to 0. Okay, so I end up with summation z to the power of n. Is this clear? Okay. And then the other term which comes from here becomes 0 because sigma is 0. Okay. And then here I have to take the derivative with respect to this term. Okay. And that will give me z to the power of sigma, natural log of z. Again, I put sigma equal to 0. So that term goes away, and all I'm left with is n times z to the power of n. Okay. Now, this c, of course we're going to get a series method, right? One is natural log of z times, probably this is your first solution. I mean, so we have to check. In the Wronskian method, we had a closed form solution. Can you tell me what this series is, z to the power of n? I'm not converting a series to a function.
Oh, z to the power of n is 1 over z? 1 over 1 minus z?
Yeah, 1 over is 1 over 1 minus z, right? When you did, so this function, this is the function form of that. What about the other one? Can I convert that? What is this? This is natural log of z times, looks like this. Natural log of z, n equal to 0 is 0, n equal to 1 is that, n equal to 2 is 2z squared, right? N equal to 3 will be 3z cubed and all that. Do you know what this infinite series is?
Is that 1 over natural, or natural log of 1 minus z?
I can take out here, let's say 1 over 2z plus 3z squared, right? Looks like that. What did you say what that function was?
Was it natural log of 1 minus z?
Not natural.
No, I was wrong.
One plus, we have to go back to this, okay, 1 plus z to the power of n is what? 1 plus nz, n times n minus 1, z squared over 2 factorial, blah, 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 right? Now, what I have is, if I put, what do I need? I need 1 minus z to the power of negative 2 also, right? 1 minus z would be this. Okay. And 1 minus z to the power of negative n would be, let's do step by step, right? Then 1 plus nz, and this has become now plus n, and this will become plus n, right? Okay, so when you put 1 minus z to the power of negative 2, what do we get? 1 minus, look at it. Oh, yeah, so 2, yeah. 1 plus 2z plus 2 times 1. Is it plus 1 or 3z squared? Do I have an extra? Oh, this is 1 minus nz. Oh, sorry, no, this is a mistake, because it is only z, right? I changed, so this does not change. N minus 1. All I have to change is z to minus z, right? So this formula is like this, exactly like that, right? Because this is even power, and nothing has happened to n, so this is that. And now what we are changing n to minus n. So n to minus n, so this is negative n, so there's negative n, so that becomes n plus 1, z squared over 2 factorial. So when you put n equal to 2, that's 2z, 2 plus 1, so that is 3z squared. So that is correct, okay. So this is nothing but, this function is nothing but, the second function is nothing but natural log of z, z over 1 minus z whole square. Alright. This is, if you this is the Wronskian method. If you got p of x, you get a functional form, right? Closed form solution. I'm just checking whatever method that it's a completely different method, right? If we got a second independent solution, a completely different method, and this is a solution. Normally you'll get a series solution. That's fine. But I'm trying to check whatever we obtained previously, whatever it's a completely different method, whether they give the same solution or not. They correspond to the same thing. So I went back to the functional form to check how it looks like. yeah, one and the same, okay. So, I'm pretty sure this is your, this is your first solution in that method, okay? I mean, natural log of z times the first solution, right? So z over 1 minus whatever our differential equation is, that is our first solution, right? And of course, that's under what we have plus something, so that gives you the second. So these are just different methods that you have to know, right? I mean, you need to know more than one method if you cannot find a solution by Wronskian. So the starting point here is the same as for Frobenius series, except we didn't keep this as a constant. We made this as a variable, and then we constructed a second independent solution. And the second independent solution is given by these two formulas. The initial roots are same, and they're divided by integer, and then you have to take the reason. Then you have to keep the recursion relationship in a very general form, rather than substituting. The older method will put sigma equal to sigma 1 and look at the series, blah blah blah. That's what we'd have done. In the older method, once you have that, you'd have say, okay, I'll just take a naught out, and then whatever, depending on what you're trying to do, right? You're trying to guess these coefficients, whether you can make sense out of it, and then substitute that already substitute calculating that you put sigma equal to sigma 1 or sigma equal to sigma 2 in the recursion relationship. We don't do that. In the recursion relationship, you keep it as a variable and try to get the functional form. If you can guess the functional form, then all you have to do is take the derivative. And you can use the other series method also, because we were having it directly in terms of derivative an with respect to sigma, right? I mean, that's all. You can use this method. You can go through this or through the other method also, which you had summation bn. What did we have? In this method was like bn, always you have, I think, bn is equal to n going from 0 to infinity, and this coefficient bn you have to calculate, right? The coefficient bn was derivative with respect to sigma of sigma minus sigma 2 times, what was the other one? An. An sigma, right? So we have to calculate. So you have the function form, you calculate that, calculate coefficient, and that would have given you this series. Okay, so you can use either method, it doesn't matter. All right, let's stop here. Okay.
There are a couple of markers up there doing
Yeah.
a dry fade.
I mean, people don't close it, and then that's what's happened.